Okay, then I should, it's my honor and pleasure to introduce our speaker today, Andreas Perea from Maastricht University. Actually, Andreas graduated, got his PhD in economics in the Maastricht University, information structures in non-cooperative games. And after some departure, he went back to Maastricht, and he's an associate professor on the Department of Quantitative Economics. I know Andres for many years back, and I know he's very interested in the foundational questions of epistemic game theory and in game theory general. So usually his talks are very deep in the philosophical sense and in the sense of IDs. So the IDs he touches, and his talks are very deep. Usually, I'm pretty sure that it is very same in this case too. So today his talk will be about the foundation for expected utility in decision problems and games. And Andres, the screen is yours.
Okay, thank you very much, Miklos. Thanks for the nice introduction, and thanks for you for all being here. So this paper addresses a very basic question, namely, what do the utilities in a decision problem or a game mean? So if we think about the decision problem, what we typically do is we write down the acts or the possible decisions in the rows, we write down the states in the columns, and for every combination of a act and a state, we write down a utility. And in the game, we actually have various such utility matrices. Namely, we have one utility matrix for every player in the game. And the acts, the decisions would be the actions of the players. And the states, so the events about which he is uncertain, these would be the action combinations of his opponents. So both in the decision problem and in the game, we do fix the utilities of the decision makers. But what we do typically not fix are the beliefs. So for instance, if you think about a game, most game theory concepts allow for various different beliefs for the players. So then what do these utilities mean if we do fix utilities, but not the beliefs? Now, many people would actually refer back to the work of Savage, but I would like to point out at least two conceptual problems of applying Savage to decision problems and games. So now one problem is that the axioms that Savage imposes, they actually lead to a unique belief. So what Savage does is he, as a primitive object, he takes the decision maker's preferences over acts, which are mappings from states to consequences. And he then imposes some, and this system of axioms then leads not only to a utility matrix or utility function that is unique up to positive affine transformation, but also leads to a unique belief. And as I already said, in the decision problem and the game, we typically do not have a unique belief. We typically do not fix the belief of the decision makers. And a second problem that I would like to point out is that in Savage's framework, the decision makers actually require to have preferences over all possible acts, so over all possible mappings from states to consequences. And that is also a bit of a problem because actually many of these acts do not really correspond to decisions in the decision problem, do not really correspond, or in the game, they do not really correspond to strategies or actions in a game. And well, because there are these two problems, well, there is something to think about here. And that's exactly where this paper comes in. So now to illustrate this problem that I just outlined, that in Savage's framework, the decision maker also has to consider acts that are not part of his decision problem. Look at this very simple decision problem here. So the two possible choices that the decision maker can make, A and B, the two possible states, X and Y, and for every combination of a choice and a state, I actually wrote down the outcome that would result. But based on these outcomes and states, one could also think about the following two acts, C and D, And as you can see clearly, these two acts, C and D, that would be part of Savage's framework, they do not correspond to choices in the decision problem, because the only choices that the decision maker, between which the decision maker can choose are the choices A and B. But Savage's framework also gives rise, for instance, to do these two different acts here, which are not part of his decision problem. Now, to address this problem, what I do in this paper is I take a different primitive object. So the primitive object in my paper is what I call a conditional preference relation. It means that for every, of course.
Can you please go to the previous slide?
Yeah, sure.
I would like to know, what do you mean by the acts C and D? So if they are allowed, so then why aren't they legitimate choices?
Because, well, it depends, of course, what you take as a primitive, right? If we write down a decision problem, let's say in a textbook, when we teach it to students, we typically write down the possible alternatives or decisions between which you can choose. We write down the things about which the decision maker is uncertain, the states, and then for every choice and every state, there is a certain outcome. But actually, Savage takes a different primitive object. For him, the primitive objects are the set of states and the set of outcomes, right? And then he assumes that the decision maker has preferences over all possible mappings from states to outcomes. So for instance, the mapping 0203 or the mapping 0401, they would be acts in the sense of Savage. But if you say, okay, the possible choices are just A and B, these two new acts, C and D, would just be, let's say, acts that could be constructed from the Savage framework, but that would not correspond to acts in the original decision problem.
And another question which is related by states, do you mean nature, states of nature, or do you mean the states of nature?
Yeah, states in general would be all events about which you are uncertain and that are beyond your control. So this could be states of nature, or if you think about a game, they could be the actions taken by your opponents. These kind of things.
Yeah. Okay, good. Thanks. I see. Thank you.
Okay. So what I do in this paper, I take a different primitive object, which I call a conditional preference relation. And a conditional preference relation specifies for every possible probabilistic belief about the states, a preference relation over your choices. So as you can already see, this has two important features. Namely, first of all, we no longer fix a belief, because we actually say, okay, for every possible belief that you could have, we specify a preference relation over your choices. Yeah? And secondly, you only have preferences over, let's say, the decisions that are relevant for your decision problem, because for every belief, we only specify a preference relation over the choices. So now the choices are actually primitive of the framework. Yeah? So the primitives of the framework are the choices and the states. So since you only have preferences about choices, we no longer have this problem, so to speak, that you have to reason about acts that are not part of your decision problem. Yeah? So these are two ways in which, let's say, my framework departs from Savage's framework. And why is it important to have varying beliefs, so not a fixed belief? So in a decision problem, your belief may actually vary because of at least two different reasons. So in a static setting, you may actually start reasoning about the possible states. And through your reasoning process, you may actually change your belief. Yeah? And or if you think about the dynamic setting, it may be that you receive some new information which rules out certain states, or actually which enables you to fine-tune your probabilities of the states. So, and this information would then induce you to revise your beliefs. Yeah? Or if you think about the game, I think the need for a variable belief is even more prominent, because in the game, you're typically uncertain about the opponent's belief. Yeah? So you may deem some opponent's beliefs more plausible than others, but in general, you don't know what the opponent's belief is. Yeah? But in this framework that I'm proposing here, if you would know the opponent's belief, so contingent on the opponent's belief, you would know how the opponent would rank his choices. That's actually also what we really mean if you write down a utility matrix in the game, right? So suppose you would know the belief of your opponent, then by looking at the utilities, you could actually derive the opponent's preference relation over his choices. Okay, so here's what I do in the paper. So I start from a conditional preference relation, and then I impose axioms on these conditional preference relations that are both necessary and sufficient for having an expected utility representation. So I really try to show what is needed on the conditional preference relation such that we can summarize it by means of a utility matrix. And the key axiom, as you will see, will be the existence of a uniform preference increase. So later we will talk about the details, but now to have an intuition for it, what does it mean? It actually means that the decision maker should be able to uniformly increase the preference intensity for one of the choices by a constant amount without contradicting his conditional preference relation. So should be able to point at a particular choice and then make this choice uniformly better relative to the other choices in a consistent way. That's what we mean by existence of a uniform preference increase. And as you will see, that will actually be the key for coming to an expected utility representation. And under certain conditions, we will also see that if we have such an expected utility representation, the relative utility differences will be unique. And this will enable us to give a concrete meaning to these relative utility differences. Namely, we could actually interpret them as preference intensities. So what do I mean by that? That the expected utility difference between a choice A and a choice B at a certain belief would then reflect the intensity by which you prefer choice A over choice B at this given belief. And this preference intensity could also be negative, which would simply mean that you would prefer B to A rather than A to B. Yeah? Okay, so the outline for this talk will be as follows. I will start by introducing the model. So what is a conditional preference relation? Then we will actually build it up gradually. So we'll start with a very specific case, the case of two choices. And then we'll see that some very basic regularity axioms are already necessary and sufficient for an expected utility representation. So that's a bit of a, let's say, a warming up. And then we come to, let's say, what I would consider to be the core of this talk, which is the case of more than two choices. And for the purpose of, since I don't have time to really tell you all the details of the paper, I decided to restrict to an important case, not the most general case, but still interesting enough, which is the case where we have an arbitrary number of choices, but where no choice weakly dominates another choice. So there's no weakly dominance, no weak dominance between choices. And then we will see that the regularity axioms, together with the existence of a uniform preference increase, will both be necessary and sufficient for an expected utility representation. And then if there's some time left, but I really doubt it, but suppose there would be some time left, I could briefly talk about two technical properties, strong transitivity and align property, which are very easily verifiable properties that can be used to check whether there exists a uniform preference increase or not. But I don't think that we'll have time for that. It would really surprise me. Okay, the model. So what are the basic ingredients of our model? We start from a finite set of acts that I call A, and there is a finite set of states that I call S. What is a belief? Well, I talk about probabilistic belief. So a belief would just be a probability distribution P on the set of states S. So by delta, I just mean the set of probability distributions on a finite set. Yeah? And the conditional preference relation, that's actually the main ingredient of my model. It's actually a mapping that assigns to every belief a preference relation over your acts, right? So for every belief that you could possibly have, there is a preference relation over your possible choices or over your possible acts. Yeah. And I must say that this framework here was actually, it's not mine, but it was first proposed by a paper by Gilbo and Schmeidler in 2003. It appeared in Games in Economic Behavior. Okay, now what is an expected utility representation? So when would we say that a conditional preference relation has an expected utility representation? It would just mean that it can be represented by utility matrix. So you can make a matrix where in the rows you put the acts, in the columns you put the states, and then in every row and column, so in every cell you put a utility, and that would then represent the conditional preference relation. So more precisely, it just means that there is a utility function u that assigns to every act and every state some real number, such that for every belief p, you would weakly prefer a to b if and only if the expected utility from choosing A would be at least the expected utility of choosing B at the belief B. Yeah, just exactly as you would expect, right? Okay, so now the purpose of this paper is to try to identify conditions on the conditional preference relation that are both necessary and sufficient for it having an expected utility representation. Okay, as I said, as a kind of warm up, we start with the case of two choices. And we will see that there we don't need very fancy axioms. Some very basic regularity axioms will already do the job. And these axioms actually already appear in Gilboa and Schmeidler 2003. Well, perhaps not literally, but at least this set of axioms here is at least equivalent to the set of axioms in Gilboa and Schmeidler. Okay, the first one is completeness. It just says that for every belief P, your preference relation over X is complete. So for every belief, you can always rank each of your acts. Yeah? Transitivity, also exactly as you would expect it, means that for every belief P, your preference relation over X would be transitive. Then continuity. Okay, what does it say? It says the following: suppose that at a belief P, you strictly prefer A to B. Yeah? You strictly prefer act A to B. And at another belief Q, you strictly prefer B to A. Then continuity says that if you then move from the belief P to the belief Q on a line, there should be a belief on that line where you become indifferent between A and B. Yeah? So if you strictly prefer A to B at P, strictly prefer B to A at belief Q, then somewhere between P and Q, there should be a belief where you become indifferent.
Andres, may I briefly
Yes.
ask a question?
Yes.
So why do you require a line here? Why not just any path?
That's a very good question. Why require a line? My guess is it would be too weak. My guess it would
really?
be that it would be too weak for an expected utility representation in combination with the other axioms. But that's okay. I would have to verify that, but that would be my guess.
Okay, thanks.
Because expected utility actually also imposes some kind of linearity, right? So in a sense, your degree of preference changes linearly with your belief. Okay, but that's again a guess. I would have to verify that, but I think it would be too weak for expected utility.
Thanks.
But it would be interesting to see what you would get, right? So, yeah. Okay. Preservation of indifference. It says that if at belief P, you are indifferent between A and B, and at another belief Q, you are indifferent between A and B, then for every belief on the line between P and Q, you would also remain indifferent between A and B. Yeah? Okay. So here you could actually perhaps do the same thing, right? Perhaps you could weaken this by saying, well, maybe there should be a path from P to Q where you would remain indifferent. Yeah, okay. And then the last regularity axiom is preservation of strict preference. It is a bit similar to preservation of indifference. It says the following, that if at belief P, you weakly prefer A to B, and if at another belief Q, you strictly prefer A to B, then if you move on a line from P to Q, then once you have left the belief P, you will always strictly prefer A to B. Yeah? So actually here you could say there are two cases. Case one would be that
sorry,
P
Andres,
always strictly prefer A. Sorry?
Andres, now you've imposed convexity, right? So now you've got convex preference.
Yeah, exactly. Yeah, that could be a different name for it. Yeah. So here actually could say that there are two cases, right? Either you always strictly prefer A to B at P. Since at Q you also strictly prefer A to B, then everywhere between P and Q you would still strictly prefer A to B. But let's say the more intricate case would be whether at P you would be indifferent between A and B, and at Q you would strictly prefer A to B. Then this says, okay, at P you are indifferent, but you're moving towards a belief Q where you strictly prefer A to B. So as soon as you leave the belief P, you already strictly prefer A to B. And that's a bit what this axiom here is saying. Okay, and then here's the theorem. It says that if you only have two acts, then the conditional preference relation has an expected utility representation if and only if it satisfies these 5 regularity axioms, so continuity, transitivity, completeness, preservation of indifference, and preservation of strict preference. Now, what is still interesting is to look at a sketch of the proof. Yeah? So I consider a case where we would have two acts, but we would have only 3 states, because then I can make some pictures. Yeah? So suppose that we would have 3 states, X, Y, and Z. So every belief, which is a probability distribution on X, Y, and Z, would then correspond to a point in this triangle. Yeah? Okay, so in this theorem, we have to show 2 directions. First of all, we have to show that if the conditional preference relation has an expected utility representation, then it satisfies each of the 5 regularity axioms. Well, this is really very easy to show. So I will not enter into the details here. That's really a very easy exercise. Now, the more interesting direction is the other one. Suppose that the conditional preference relation satisfies the 5 regularity axioms, then we have to construct, or at least we have to show that there is a utility function that represents it. And we'll actually, all the proofs in my paper are constructive in the sense that I always construct a utility function that represents the conditional preference relation. And that's also what I will do here by this proof sketch. So suppose that without loss of generality at state Z, let's say you strictly prefer A to B. So A and B are the 2 acts. At Z, you strictly prefer A to B. At X, you strictly prefer B to A. And at Y, you also strictly prefer B to A. Okay, now, since at X, you strictly prefer B to A, and at Z, you strictly prefer A to B, then by continuity, there should be a belief between X and Z where you are indifferent between A and B. Yeah? So perhaps here. The same here, at Z you strictly prefer A to B, at Y you strictly prefer B to A. So there must be a belief between Y and Z where you are indifferent, let's say here. Okay, so far we have used continuity. Oh, by the way, yeah, of course, this transitivity and completeness, I just assume it in the background. They're so basic that, okay. I mean, really the key axioms here are continuity, preservation of indifference, and preservation of strict preference. Okay, so far we have used continuity. Now, here we have a belief where you are indifferent between A and B. Here you have a belief where you are indifferent. So then we can use preservation of indifference and then say, well, for every point on this line, for every belief on this line, you will also be indifferent between A and B. Yeah, okay. And now we can use the last axiom, preservation of strict preference. Namely, take any belief here. I don't know, can you see my cursor, by the way? Yeah, okay. For every belief here, it can be written as a convex combination between, let's say, state Z and the belief here where you are indifferent. Since at Z, you strictly prefer A to B, and on this line, you are indifferent, and since every belief here can be written as a convex combination of these 2, by preservation of strict preference, for every belief here, you will strictly prefer A to B. Yeah. Mm-hmm. And we can do a similar thing here. Every belief in this lower area here can be written as a convex combination of a belief here, where you strictly prefer B to A, and a belief here, where you are indifferent. So by preservation of strict preference, for such a belief, you will always strictly prefer B to A. Yeah? So by using the 3 axioms, we have now shown that the picture for the conditional preference relation must look like this. Okay, now it's time to construct the utility function that will represent it. Now, the utilities for one of the choices, let's say A, they can be chosen arbitrarily. Doesn't matter. Yeah? So suppose we've already chosen utilities for A at the states X, Y, and Z. Now, how do we now have to choose the utilities for B at the states X, Y, and Z, such that we represent this particular conditional preference relation here? Okay, well, one thing is clear. At this belief here, we must set the expected utility of B equal to the expected utility of A, because you must be indifferent between A and B. Also here, we must set the expected utility of B equal to the expected utility of A, because you are indifferent. And here we must make sure that the expected that utility for B at state Z is smaller than the utility for A. Yeah? Now, in fact, these three conditions here, they can be formalized as a system of linear equations with three equations and three variables. Okay, why is that? Well, what are the three variables? The three variables are the utilities for B at the states X, Y, and Z. These are the three variables. Now, by requiring that the expected utility for B at this belief P should be equal to the expected utility of A, that's one linear equation. Here we get another linear equation. And if we fix, let's say, here a number alpha less than the utility of A, and set the expected utility of B equal to alpha, this gives a third linear equation. So in total, we get three linear equations with three variables. And since these three beliefs here are linearly independent, the three equations are linearly independent. So three linearly independent equations with three variables, hence we get a unique solution. Yeah? So we can choose utilities for B such that this is indeed satisfied. Yeah? But then, okay, the rest actually then easily follows, because on this line, since here the utility of B is equal to the utility of A, here also, everywhere on this line, the expected utility of A and B are equal, as it should be, because everywhere on this line, you are indifferent between A and B. And here, since the utility of B is less than the utility of A, here the utility of A is equal to the utility of B. Everywhere here, the expected utility of B will be less than the expected utility of A, should be, because you strictly prefer A to B. And finally, by construction, it also follows that in the lower area, the expected utility of B will be bigger than the expected utility of A, as it should be, because you prefer B to A. Yeah. So that's, in a nutshell, how the proof would work for two choices.
And it also works for, if I may interrupt, sorry, for any number of states, because then you have a simplex and each number adds a new dimension. So you have all these linear equations, the independence. So on each edge to the new state, you could get a new independent value. Yeah,
very good point, Bernard. So if you have an arbitrary number of states, right? Let's say you have n states, then you would actually have n linear equations with n variables. And yeah. So, and also let's say the set of beliefs where you are indifferent, that would be an n-1 dimensional hyperplane. So you can actually choose n-1 linearly independent beliefs on the indifference hyperplane, and then you choose one other beliefs where you have a strict preference. So you have n linear equations with n variables, and actually, since the n beliefs are linearly independent, the n equations are also linearly independent. And yeah, you would again get a unique solution. Yeah. Okay. So now we move, let's say, to the core of this talk, which would be the case of more than three choices. Because then things, yeah, we have to think about something deeper than these regularity axioms. Okay, let me first try to explain why the regularity axioms are no longer enough to guarantee an expected utility representation if you have more than two choices. Okay, so here's an example. Here I have an example with three acts, A, B, and C, and again, three states, X, Y, and Z. And for every area here, I have specified the preference relation over X that you would have. So for all beliefs here, you would prefer C to A and A to B. For all beliefs here, you would prefer C to B, B to A, and so on. And these three lines would be the lines where you would be indifferent between a pair of choices. Okay. Now, it's easy to see that this conditional preference relation here satisfies all the regularity axioms. It's complete, it's transitive, it satisfies continuity. satisfies preservation of indifference, satisfies preservation of strict preference, so all the regularity axioms are satisfied. However, we do not have an expected utility representation here. Now, why not? Now, to see this, it's really important to see what happens outside the belief simplex. So what I'm now going to do is I'm going to extend the lines where you are indifferent between two choices. I'm going to extend these lines linearly outside the belief simplex and then see what happens. So if I do that, I see the following. Okay. Now here, this is already enough to show you that we can never have an expected utility representation here. Why? Well, suppose that we would have an expected utility representation. I will show that this leads to a contradiction. Now, here on this line, since you are indifferent between A and B, the expected utility of A and B must be the same. But then they must also be the same outside the belief simplex on this line, right? Because expected utility is something that you can generalize outside the belief simplex. Right? So inside the belief simplex, all probabilities are positive, but expected utility could also, at least mathematically, be defined for negative probabilities. So you could also extend it outside the belief simplex. So everywhere on this line, the expected utility of A and B, they should be the same. Similarly, here you are indifferent between B and C. So even if you extend this line outside the belief simplex, the expected utility of B and C should be the same. But now we see the following. In this point here, outside the belief simplex. So it's not a belief, right? Because some of the probabilities are negative, or people would call it signed probabilities maybe. But for this point here, the expected utility of A and B would be the same. The expected utility of B and C would be the same. Hence, the expected utility of A and C would be the same. But then, if you look at this point here, let me see. Okay, yeah. If you look at this point here, this is on the line in the belief simplex where you are indifferent between A and C. So here, better the expected utility of A and C, they better be the same, right? So also here, the expected utility of A and C must be the same. But then everywhere on this green line, the expected utility of A and C should be the same. But it's a contradiction because here you actually prefer C to A. So the expected utility of C and A should not be the same. So we get a contradiction here. And well, as I think some people will already notice, the reason why this really went wrong, at least geometrically, was that these three lines, right? So if we extend the lines where you are indifferent between a pair of choices, if we extend these three lines outside the belief simplex linearly, they did not coincide in the same point. They did not intersect at the same point. And that's actually the reason, as we will see, why the expected utility representation fails. Yeah? They should actually have met at the same point. Okay, I hope this example was clear. So we need something more than irregularity axioms for expected utility to work for more than two acts. Yeah. Okay, so now conceptually, so not mathematically, but conceptually, what is actually wrong with this conditional preference relation here? Because, yeah, if you just look at it for a few seconds, right, especially if you don't look outside the belief simplex, everything looks pretty normal, right? All the regularity axioms are satisfied. Yeah, I mean, you don't quickly see something that is really wrong about it. But as I said, I mean, it's really important to look what happens outside the belief simplex here. But okay, let's now try to reason inside the belief simplex and try to see conceptually what is wrong with this conditional preference relation. Now, what is wrong is that somehow, as we'll see in a minute, it's not possible for the decision maker to uniformly increase his preference for act A without contradicting his conditional preference relation. So it is not possible for the decision maker to uniformly increase the preference intensity for act A relative to B and C by the same amount without contradicting this conditional preference relation here. Now, why is that? Okay, so what would it mean that you actually uniformly increase the preference for A? Well, first of all, it means that, okay, there should be some number alpha such that for every belief, you increase the preference intensity of A relative to B and the preference intensity of A relative to C by the same amount alpha. Okay, so what would this mean geometrically here? It means that if you compare A to B, if you uniformly increase the preference for A, it means that you make A better, right? So there should be more beliefs where you prefer A to B. So somehow the indifference line, where you are indifferent between A and B, that indifference line should be moved towards the right, yeah? So for instance, by this factor here. And moreover, since for every belief, you increase the preference intensity of A relative to B by the same amount, it should not be just an arbitrary shift, it should be a parallel shift of this indifference line. So the indifference line where you are indifferent between A and B, if you make A uniformly better, it should shift in a parallel fashion to the right. So it should get something like this. So this blue line would now be the new line after uniformly increasing the preference for A, where you would be indifferent between A and B. And everywhere above this blue line, for all the beliefs here, you would now prefer A to B. So there would be more beliefs now where you would prefer A to B relative to before. Yeah? Okay, now we can do the same if you compare A to C, right? So if you uniformly increase the preference for A, it means that also the set of beliefs for which you prefer A to C, that set of beliefs should also become bigger. So also this indifference line here should shift to the right. Yeah. And since for every belief, the preference intensity between A and C increases by the same amount, it should be a parallel shift. So you should shift this indifference line parallelly towards the right. But now we can say a little bit more. And now this is the crucial thing, really. What's the crucial thing is that the intensity by which you prefer, by which increase, the amount by which increase the preference intensity of A compared to B should be the same as the amount by which you increase the preference intensity of A compared to C. So somehow the degree by which you make A better relative to B should be the same as the degree by which you make A better relative to C. So these two...
May I briefly interrupt? So
yeah,
what is the ordinal analog of this intensity of this alpha?
Yeah, it's really like a cardinal notion. Yeah.
Okay.
It's a bit like a cardinal notion. I use it more like a kind of an intuition for the axiom. But yeah, but I try to explain at least in geometric terms by the shift of this indifference line. And
that's fine once we have a utility representation. But how do we express this for the preferences themselves, which are purely
okay?
ordinal?
Then that will actually become clear, I hope, in the next slide, on the next slide, when we come to the definition of a uniform preference increase. I hope this will clarify things. If not, then please ask me again.
Okay,
yeah?
Thanks.
Okay, so we have to shift the line where you are indifferent between A and C also towards the right. But now we can say a little bit more. Since the amount by which you increase the preference intensity between A and B should be the same as the amount by which you increase the preference intensity between A and C, we should shift this indifference line here by exactly the same red vector here. Okay, let me explain now why this is. What is special about this red vector? This red vector actually goes from a belief where you are indifferent between B and C to another belief where you are indifferent between B and C. So these are two beliefs where your preference intensity between B and C are 0. So when you move along the red vector, you don't change your preference intensity between B and C. The only thing that can change is the preference intensity between A and B and between A and C. Now, here we change the preference intensity between A and B. Since you don't change the preference intensity between B and C, it must be the case that you have changed the preference intensity between A and C by the same degree as the preference intensity between A and B. Right? So, okay, let me explain. If you increase the preference intensity between A and B by an amount, let's say alpha, if the preference intensity between B and C remains the same, then this means that the preference intensity between A and C should also have changed by the same amount alpha, right? And that's exactly the key here, so that this indifference line, where you are different between A and C, should be shifted by exactly the same vector, the same red vector here. Yeah. But now you can see where the problem is, because in this new conditional preference relation, represented by the blue lines, where you have uniformly increased the preference for A, we have actually a belief here, the blue belief, where you are indifferent between A and B, indifferent between A and C. But since we have only changed the preferences between A and B and A and C, but not between B and C, you should also be indifferent between B and C at the blue point, but that's not the case. So we are violating transitivity here. And that's, at least geometrically, the reason why in this particular example, the decision maker cannot uniformly increase his preference for act A without contradicting his conditional preference relation.
Can I ask a quick clarification?
Yeah, sure.
Yeah. You said in the beginning that this applies to games as well as to decision problems. So different acts can be to different individuals, to different players.
Mm-hmm.
So yes.
Different acts, yeah, but here I'm viewing everything from the perspective of one particular player.
Yes, but in general, in your framework, is it important that, can it be that different acts belong to different individuals, to different players?
Okay, yeah, I understand your question. So for this paper, it's not really that important. So what I do is I analyze a game as if it were a one-person decision problem by just putting myself into the shoes of one particular player. Yeah. So this particular player, what are his acts? His acts are his actions in the game. What are the states? The states would be the action combinations of his opponents. Yeah. And of course, every player would have a personal decision problem. But somehow this does not really play a major role in my analysis. So I just really focus on one particular player in the game. Yeah.
Andres, sorry, may I have a question? So if I understand correctly, if you extend the domain of your analysis to all the norm measures, so norm distributions, signed or not signed,
yeah,
then from the old axioms, your original axioms, you get the very same. So your problem, what you are doing is just by this uniformly increase the preferences stuff, just you somehow bring this wrong intersection into the simplex.
That's a very good question, Miklos. What you're saying would be correct if you, let me see, now I have to be careful. What you say would be correct on the two conditions. First of all, that there would be no weak dominance relationships between the acts. That's one thing. And secondly, that there would only be 3 acts. Okay, this example is for 3 acts here, right? But if you move to more than 3 acts, then what I showed here in this picture would actually no longer be enough to guarantee expected utility representation.
Okay, so it means that it is not only the problem that your domain is somehow restrictive.
No, it's for more than 3 acts, it's a bit deeper than that. Yeah.
Okay, thank you.
Yeah. Okay, so I think now it's time to give a formal definition of a uniform preference increase. Okay, just move this here. Okay, so let me again return to this example where we have 3 acts, A, B, and C, and the 3 states X, Y, and Z. Now, uniform preference increase, okay, the intuition is that you uniformly increase the preference intensity for choice A by a constant amount. So for every belief and relative to every other choice, you increase the preference intensity for choice A by the same amount, let's say alpha. Okay, let's normalize this amount alpha to 1. So suppose we uniformly increase the preference intensity for A by 1. Now, what consequences does this have? Well, here, on this line, you are indifferent between A and B. So the the preference intensity between B and A would be 0, because you would be indifferent between A and B. And so when I say preference intensity equal to 0, it means you would be indifferent between the two choices. Yeah? Now here, this blue line, that would actually be the beliefs where you would be indifferent between A and B in the new conditional preference relation, where you've already uniformly increased the preference for A. Okay, now what does this mean? Here, you would, in the blue line, you would be indifferent between A and B if you would already have made A better by degree 1 relative to B. Yeah? So this means that in terms of the original conditional preference relation, on the blue line, you would actually prefer B to A by intensity 1. Okay, okay, that's important to understand, so let me repeat this. So in the uniform preference increase, so when you go from the black line to the blue line, right? So what you have done is you have uniformly increased the preference density for A by 1. Now, on the blue line, after doing that, you would be indifferent between A and B. So before making A better, so when you look at the original conditional preference relation, on the blue line, you actually preferred B to A by intensity 1. Yeah. Okay, and now let us take a belief P, which can be written as 1 minus lambda times a belief on the black line, where you are indifferent between A and B in the original one, and lambda times a belief on the blue line, where you are indifferent between A and B in the new conditional preference relation. Yeah? For instance, here. So geometrically, it would look like this, right? So this is just saying the same thing as here. Oh, by the way, P, A, B, that actually means a set of beliefs where you are indifferent between A and B under the original preference relation. And this here would be the set of beliefs where you are indifferent between A and B under the new conditional preference relation where you have uniformly increased the preference for A. Yeah? Okay, now what can we say about the degree or the intensity by which you prefer B to A at the belief P? Well, let's see. Here, the intensity by which you prefer B to A is 0. Here, it's 1. Now, the distance between this black belief and P here is lambda times the distance between the black belief and the blue belief. If you go from the black belief to the blue belief, the preference intensity between B and A increases by 1. Since here you travel lambda times as much, the intensity by which you prefer B to A at the belief P should be lambda times as much, so it should be lambda. Yeah? So here I'm actually assuming that preference intensity is linear in belief. Yeah? Now we can do the same when looking at the ordered act C. Yeah? So suppose that for the ordered act C, we also have a new line where you are indifferent between A and C under the new conditional preference relation, where you have uniformly increased the preference for A. Yeah? Now, suppose that P can be written as 1 minus mu times a belief on the black line, plus mu times a belief on the blue line. Yeah? So we have something like this. Now, the same as previously, on the black line, since you are indifferent between A and C, the preference intensity between C and A will be 0. In the blue line, after uniformly increasing the preference for A, you have become indifferent between C and A. So under the original conditional preference relation, you should have preferred C to A by intensity 1. And since the distance between this belief here and P is mu times the distance between these two, here the preference intensity between C and A has increased by 1. Since here you travel mu times as much, here the preference intensity between C and A should be mu. Yeah? But now comes the crucial thing. This belief P was not an arbitrary belief. This belief P here was a belief where you are indifferent between B and C. So intuitively, if you are indifferent between B and C, it means that the intensity by which you prefer B to A should be the same as intensity by which you prefer C to A. So this lambda should be equal to mu. Yeah? And that will actually be the key for our definition of uniform preference increase, namely that once you have defined a new conditional preference relation where you have lifted the preference intensity for choice A by a constant amount, then for every belief in the belief simplex, we can actually calculate the intensity by which you prefer B to A or C to A at that particular belief. Now, the beliefs where you are indifferent between B and C, these should be exactly the beliefs where the intensity by which you prefer B to A is the same as the intensity by which you prefer C to A. Yeah? That will actually be the definition of a uniform preference increase. Okay, I will spell it out here. So that's actually the key definition for this talk. Then, okay, this will also be little time left then for other things, but at least I want you to understand this definition here. So what is a uniform preference increase for A? It means that you define a new conditional preference relation indexed by a prime. We say that it uniformly increases the preference for A relative to the original one if, first of all, this conditional preference relation satisfies all the regularity axioms. Okay. Secondly, that since you're actually making A better in a sense relative to before, there should be more beliefs relative to before where you prefer A to B, right? So if under the original preference relation, you preferred A to B at a belief P, then under the new conditional preference relation, you should actually strictly prefer A to B at P. Yeah. So the set of beliefs where you prefer A to another choice should become bigger. Yeah. Now, this condition here says that for every belief P in a belief simplex, there should be a unique number lambda such that P can be written as 1 minus lambda times the belief on the black line plus lambda times the belief on the blue line. So this condition here is the guarantee that for every belief P, we can uniquely, let's say, derive the intensity by which you prefer B to A at belief P. Because this number lambda, we will just call it the intensity by which you prefer B to A at P. Because that's actually also what we did on the previous slide. We saw that if the picture is like this, then the intensity by which you prefer B to A at belief P is exactly lambda. And now the crucial condition here is this one. Oh, by the way, condition C, the geometric interpretation of this condition is that in the new conditional preference relation, the set of beliefs where you are indifferent between A and B should be parallel to the set of beliefs where you were indifferent between A and B in the original conditional preference relation. So there should always be a parallel shift of the indifference sets. And then the last condition says that the beliefs where you are indifferent between B and C, remember, we are only increasing the preference for A. We're not changing the preferences between all other choices. So the beliefs where you are indifferent between B and C should be exactly those beliefs where the intensity by which you prefer B to A is the same as the intensity by which you prefer C to A. So this means that the lambda here should be the same as the mu here. So here we should have lambda, here we should have lambda. Yeah? So that's the definition of a uniform preference increase. And well, actually, in this picture, it has some interesting geometric consequence. Namely, if there is a uniform preference increase, then it actually follows that these, if you extend the lines of beliefs where you are indifferent between A and B, B and C, and A and C, if you extend these three lines outside the belief simplex, then they will always coincide, they will always intersect at one and the same point. That's actually a consequence of this existence of a uniform preference increase here. So the axiom that I'm proposing is the existence of a uniform preference increase. It says that if we look at the conditional preference relation, then there should be a uniform preference increase for at least one of the acts. So it should, the decision maker should always be, it should always be possible for the decision maker to uniformly increase the preference intensity for one of the acts, right, relative to the original one, without contradicting his conditional preference relation. And we'll see that if there are no weak dominances between acts, then this new axiom in combination with the regularity axioms will actually characterize precisely those conditional preference relations that have an expected utility representation. So when would we say that an act A is weakly dominated by an act B? It just means that for every belief P, B is always weakly better than A, and there is at least one belief where you strictly prefer B to A, right? So the theorem says that if there are no weakly dominated acts, so this means that whenever you compare two acts, there will always be a belief where you prefer A to B and another belief where you prefer B to A, right? Then a conditional preference relation has an expected utility representation if and only if it satisfies the regularity axioms and the existence of a uniform preference increase. Yeah? So existence of a uniform preference increase is both necessary and sufficient in combination with regularity axioms to guarantee an expected utility representation. I think it's more or less time to finish. So, okay, let me perhaps show you one more slide. Just this one. Actually, it's said that if there are no weakly dominated X, right, then the relative utility differences would be unique. So that's actually shown in the theorem here. It says that if there are no weakly dominated X, and if not all the sets of beliefs where the decision maker is indifferent between two choices, if these sets of beliefs do not all coincide, then the following is true, that if we have two different utility representations, U and V, then there is always a positive number alpha, such that the expected utility difference in U are always alpha times the expected utility differences with respect to V. Or in other words, the relative expected utility differences are uniquely given in this case. And in that case, one can really view these expected utility differences between A and B at belief P as the intensity by which the decision maker prefers A to B at belief P. Because these expected utility differences are unique up to a positive multiplicative constant. So yeah, at least in relative terms, they are uniquely given. Okay, and I think here I should really stop, but of course my time is up.
May I just ask one more question about the axiom?
Yeah.
So your axiom is then actually stated as an axiom about cardinal utility and not really about the ordinal preference relations.
Let me see. Yeah, I mean, perhaps the cardinal aspect is here because of this lambda, right? This is really the cardinal thing here. Yeah. Yeah, at least I would indeed agree that there is some cardinal element in the definition of a uniform preference increase. But on the other hand, I would also say that it's still a long way, let's say, between, let's say, talking about uniform preference increase and talking, let's say, about the expected utility representation. There's still a long distance that one has to travel there. But I agree that at least there is some cardinal component here. Yeah. Yeah. Yeah.
I wonder, you know, exactly looking here at condition C, in a sense, you're saying, so there is a fictitious new preference prime
Yeah.
that can be represented by some other new belief. I mean, new combination of states, right? I mean, that's you essentially mimic this whatever you call it, preference prime, by some shift in belief of what's going on, and you require a certain consistency about this. I mean, that's how I would interpret it.
Yeah.
And so, because I mean, intensities are very tricky because you don't really compare like pairs of and so on. So I would try to get away from that. But my impression is that when you look at C, it's more or less, I mean, in the von Neumann-Morgenstern axioms, the relevance of alternatives. I mean, that's what I suspect is happening. That's exactly, you have a certain substitutability. I mean, C and D together, in a sense, mimic that you have the same. I mean, if you do that, if you have a fictitious new increase in preference that corresponds to a certain shift in your beliefs, then that has to be consistent. I mean, that's what I suspect is going on, more or less. I mean, at least mathematically. I'm not sure about the interpretation, but that's...
Yeah, at least, yeah. I would say, roughly speaking, if you look at the big picture, that is indeed quite a good summary of what is going on. I mean, and complete comparison with Van Orban and Morgenstern is a bit limited here because you see, in a sense, okay, if you compare my framework to that of Van Orban and Morgenstern, there is some similarity, because what you can do is the following. If you take an act and fix a belief, then this act in combination with the belief can indeed be indeed corresponds to a probability distribution over outcomes. So it would correspond to a Van Orban Morgenstern lottery. Mm-hmm. However, Van Orban Morgenstern actually require that the decision maker is able to compare all different lotteries with each other. Here,
yeah, but that's already,
I don't require. Here I don't actually require less, because here I only require that you compare lotteries that actually arise from the same belief, that actually have the same underlying belief over the states.
Yeah, but not quite, because you're introducing this fictitious belief here in the alpha and sorry, when you postulate that A is indifferent to B under this tilde prime condition, then in a sense you introduce the possibility of introducing a new kind of belief to represent that. That's what I think. And in Van Orban Morgenstern, you would have, actually it suffices to combine only simple lotteries, meaning you take one or the other outcome, and then, because then it's already unique. I mean, you have that is already completely induced once you have simple lotteries. I mean, the utility function is completely determined. So you don't have to actually specify your preference for all these lotteries. You can just assume certain abstract substitutability. Anyhow, I don't want to.
Yeah, no, but I do agree that there are some similarities there. Yeah, but that okay. We should dive a little bit deeper into that. Yeah. Thanks.
Can I ask question directly, or how does it work? Sorry. Can you hear me?
Miklos, I think.
Sure. Go ahead, please. Yeah.
Can you hear me?
Sure. Go ahead.
Okay, great. So actually, my question was very much related to Bernard's question, and we with Lorenzo, we are working on some conditional acts, and we are trying to understand your framework, whether or not, or in what sense we should use your foundation for for our paper as well. So once in a game setting, in a strategic game setting, once you fix the strategies of the other individuals, possibly mixed strategies, it induces obviously a utility function. So in that case, once we fix the beliefs of the others, does the framework boils down to your own framework, or your axioms characterize the utility function in that case? So is there the similarities works that way, or how should we understand it?
I'm not sure I completely understand your question. So what do you mean by, obviously we would have, you say that once we fix the strategies of the other players, obviously we would have utility representation.
So in a mixed strategy extension of the game, right? We have preferences over consequences, and multilinear extension of this game. Let's say, it gives a standard mixed extension of a game. So let's suppose in this game, let's fix a strategy profile except I. So a sigma minus I, a probable distribution for other players that induces in this game, expected utility function for me, or it is a conditional preference basically, right? And in that case, the utility function that you derive should give the same kind of utility function.
Okay.
You see what I mean?
Yeah, I hope so. Okay, I think I can say this. So here, I assume that the decision maker, right, or the player, only chooses pure strategies, right? So not mixed strategies. But once you actually satisfy the axioms here, and once you have an expected utility representation, then you can also look at the multilinear extension, where players are allowed to choose mixed strategies. So I don't think that there's a big difference. So I don't think much would change if I would allow decision maker to randomize over his acts. I don't think there would be any major differences there. So that's something that you could add at the end. Let's say, so if you first do this analysis, if you're then interested in a case where decision makers could randomize, then I think that should certainly be possible. Yeah.
Okay. Yeah. Thanks a lot.
Andres, so may I have a simple question? So what if in this example on your screen, these black lines, these parallel lines, A indifference B and A indifference C are parallel to the B indifference C? The distance from them are different.
I'm sorry,
so why is this not okay? So I mean that you have these black line segments, A indifference with C, and this is parallel to the B indifference to C, and the A indifference to B is also parallel to the B indifference B.
Wait a moment, I'm a bit lost now. Because
okay, so you have three line segments, those are the indifferences.
Yeah, yeah.
What if those are parallel to each other?
What if those are parallel to each other? Okay, yeah, it's a very good point. Okay, very good point. Then at least in this picture, they would not intersect, right? Because they would all three be parallel. But there is also still an area, let's say, below the belief simplex that I did not draw, right? So, okay, what you can still do is to look at the linear spans of these three lines, right? Linear spans are linear spaces. So they at least contain the zero vector, right? Mm-hmm. And these linear spans will always have a non-empty intersection because the zero vector will always be in the intersection. Yeah? Mm-hmm. But if these three lines are parallel,
you mean that at least they meet at the origin?
Yeah, exactly. But the origin is not drawn here in this picture. Here I only look, let's say, here I only extended the belief simplex to vectors where the sum of the probabilities is equal to 1, but where some of the probabilities may be negative, right? But so if the three lines are parallel, then you still can look at the linear spans of these three lines. These would be linear spaces. And then the intersection of these three linear spans would then be a line through the origin that would actually be parallel to the belief simplex.
So somehow you mean that that if there is no intersection, it's not a problem.
No, and mathematically it's not a problem because the linear spans of these three sets, they would still intersect. They would still have a common intersection.
But that is a trivial one. So of course we have
a trivial one. It would still be a line through the origin, but this line would now be completely parallel to the belief simplex. So it would be completely below the belief simplex. So I could not really draw it here on this two-dimensional picture.
And then other questions very related to previous ones. So it seems to me that in you model the probability distributions, okay, you call them beliefs, but are primitive. So somehow you have this objective risk or whatever in this model, or you can interpret it at least in this way. So you mean if you compare it to, and this is the, the von Neumann-Morgenstern setting is the canonical one for this. So if you compare your setting to those, that von Neumann-Morgenstern, you say that perhaps one of the differences at least that you don't compare each lotteries to each other. You mentioned to Bernard. Only you, if I understand correctly, you argue that you take some so-called lines and you just compare the lotteries over the lines to each other, something like that. So you have a space of lotteries and you don't compare to each other, each of them, that's only some segments.
Yeah, exactly. Yeah. So you only compare those lotteries that could arise from the same probabilistic belief about states, right?
Yeah.
And because if you fix a belief, right, then each of your acts generates a different probability distribution over outcomes, right?
Yeah.
And these are then the acts that you can compare that actually belong to the same belief about states. Whereas von Neumann and Morgenstern actually require the decision maker to also rank lotteries, to rank all possible lotteries.
All.
So that's one important difference.
And what if you try to translate this property to that von Neumann-Morgenstern setting? So perhaps it turns out that, you know, that.
Yeah, but then I would run into conceptual problems, right? Because here in the primitives in my model was a set of acts and a set of states. These are my primitives. And so I wanted to stick as closely as possible, let's say, to decision problems and games. Whereas, let's say, the von Neumann-Morgenstern framework, there the primitive object is actually a set of outcomes. That's a primitive object, and then all probability distributions over those outcomes.
Yeah, so the mixings, the lotteries, yes, or the mixings in general, yes.
So yeah, if I would then take the von Neumann-Morgenstern framework and apply it here, then I would.
No, I would apply your result in the von Neumann. I ask you, or I just wondering about that, applying your result in that setting, not
the other way around.
Result in your setting.
Yeah, I think at least mathematically it could be embedded, right? So I think in principle I see no reason why that could not work, because yeah, at least mathematically, a subjective probability distribution is no different from an objective probability distribution.
Yeah.
So I don't think that matters from a mathematical point of view. So I think that this framework could indeed be embedded into the von Neumann-Morgenstern framework, and yeah.
Anyway, yeah, I don't think that you can just answer this question prompt, but yeah, that result was interesting, and perhaps we can learn something about von Neumann-Morgenstern by your result. That's what I mean. Further questions or remarks or? And thank you very much again for your talk, for your very interesting talk, and take care and see you and whatever. Thank you very much.
Okay, thank you. Thank you.
Thank you.
Thank you.